All right, welcome. We are finishing up chapter 1 with section 1.7. These are integrals resulting from inverse trigonometric functions. Step 1, let's just remember what an inverse trigonometric function does. So here we have f of x is equal to sine inverse of x. Now, sine inverse in general, if we have the unit circle, and that's not a very good circle. If we have our unit circle, and we have this point, remember it's like an x and a y. Usually we plug in some angle and it produces, in this case for sine, it produces that y value. So sine inverse allows us to go the opposite way. Okay, so sine inverse allows us to say, hey, I know what value I have on the unit circle. Like for instance, sine of, we can do pi over 6 is 1/2. Right? The sine value at pi over 6 is 1/2. So sine inverse of 1/2 should give you, say, what angle gives you the y value, the sine value of 1/2? Well, pi over 6. Okay. For sine, you only want to look at these angles here. You don't want to go past the 90 degree or pi over 2 mark, because then you have two matching y values. And so usually we'll say we restrict the domain here. Excuse me. Usually we would say we would restrict the domain of sine inverse from negative pi over 2 to positive pi over 2. So you'll see things like that as you start looking at sine or sine inverse. You'll see some interesting little things that get attached to it. Well, our goal is to review how to find the derivative of sine inverse. We know the derivative of sine, but how do we find the derivative of sine inverse? Well, let's start there. Y equals sine inverse of x. That's what we currently have. If we rearrange this thing, that means x equals sine of y. Okay? X equals sine of y. Therefore, if we're taking the derivative, if we take the derivative with respect to x of both sides, derivative of x is just 1. Now, derivative of sine of y, since that is not an x that's inside of there, we do take the derivative. Derivative of sine is cosine of y, but we don't know the derivative of y itself. So we add that dy dx, the derivative of y with respect to x, kind of has to get chained on that chain rule idea. All right, so we are then trying to solve for this thing. We want to solve for the derivative of y. That's our goal, right? F prime derivative of y with respect to x. So we divide by cosine y. All right, so I got 1 over cosine y is equal to dy dx. And then this is where things get a little crazy. Do you remember our Pythagorean identity? Sine squared plus cosine squared is equal to 1. Well, solving this thing for cosine squared, getting rid of that squared, we've got cosine y equals 1 minus sine squared inside of a square root. Technically, we do want the plus or minus that's in front of that. When we replace, we can say, hey, remember sine of y? Sine of y is equal to x. So this entire derivative is 1 over cosine y gets replaced with this. Sine y is actually x squared. And we are here. We don't need the negative version, seen as the sine inverse function can only be from that negative pi over 2 to pi over 2. It kind of just restricts that, so we just really have to worry about the positive side. And there we go. That's our sine inverse function derivative. Now, there were more. There was a cosine inverse derivative, a tangent inverse derivative. Those are on our formulas pages, all right? You would have done them a little bit. Notice the sine inverse formula and the cosine inverse derivative. They are pretty much the same formula, just a negative out in front. Tangent and cotangent derivatives, inverse derivatives are same idea, just a negative in front. And secant and cosecant derivatives are also the same, just with that negative in front. All right, so if the idea is that these are the derivatives of this, if I integrate this, well, I should get this if I take the antiderivative. And that's really what we are dealing with here in this section. If I have an integral that looks like this, kind of looks like this thing, I expect to get sine inverse. Now, when there are additional numbers besides just 1, we can still do this. That a number there is just, a is a number, and that u is our variable. Slightly different than a u substitution that we've been doing. But just remember, hey, a is some number. It's always going to be some value squared. Okay, so to try these out, we are trying to basically just follow one of these 3 formulas and do this integral. All right, so we are integrating from 0 to 1/2 of dx over the square root of 1 minus x squared. Well, that is pretty much that exact formula. Our a is equal to 1, and our u is equal to x. 1 squared is 1, and u squared is x squared, or x squared is x squared. All right, so we basically just go straight to this formula. It becomes sine inverse of u, which is x, over a, which is 1. Now, we don't need the plus c because this is a definite integral. We want to put in 1/2 and 0. So don't really need the divide by 1. So we're doing the sine inverse of 1/2 minus sine inverse of 0. And let's see if we can handle this. Sine inverse of 1/2. Is there a value on the unit circle that gives us the answer of 1/2 for a y? All right, 1/2 for a y on the unit circle, pi over 6. And then we had sine inverse of 0. Y is 0 at the angle 0. So we got that. This is pi over 6 minus 0. So the answer there, pi over 6. All right, next one here. I am seeing the integral of, should be like 1 over 1 plus x squared. Well, that's that. Okay, here we have again our a is 1 and our u is x. So to do this integral, it would be 1 over 1 tan inverse of x over 1. From radical 3 over 3 to radical 3. So all the ones aren't super important. So we're doing tangent inverse of radical 3 minus tangent inverse of radical 3 over 3. Remember, tangent is a y divided by an x. So I'm looking for a y divided by x that gives me radical 3. Well, when I take a y divided by an x and I want a radical 3, that's going to be that coordinate pair right there. If I do the square root of 3 over 2 divided by 1/2, same change flip, so radical 3 over 2 times 2 over 1. That's the radical 3 that I need. So tangent inverse of radical 3 is pi over 3. And tangent inverse of radical 3 over 3 is actually that right there. If we do the 1/2 divided by radical 3 over 2, we get 1 over radical 3. If we rationalize, we get that radical 3 over 3. So pi over 6 for that answer. So we got to do pi over 3 minus pi over 6. Well, pi over 3, that's 2/6 minus 1/6 is pi over 6. And that is the big idea there. There are 2 more problems. Oh, yep, we should probably do them. All right, looking at this problem, not a definite. Just need to find this antiderivative. It looks like this formula here. Okay, so we're trying to put this, our a, what squared is 4, and our u, what squared is 9x squared. Well, 3x. So when we do our sine inverse of u over the absolute value of a, 3x over the absolute value of 2 is 2. We'll put our plus c, and that is our integral. All right, the next one looks like our a is 2, our u is just an x, and that's a tangent inverse. So we've got tan inverse of, actually 1 over a of x over a, and we want from 2 to 0. 2 over 2 is 1, and 2 over 0 is 0. Tangent inverse of 1. When will tangent be 1? Well, tangent's 1 at the 45-degree angles, the pi over 4's. Tangent y divided by x, so something divided by itself is what gives you 1. All right, so pi over 4. And tangent inverse of 0. Tangent of what gives you 0? Well, that answer is actually 0. All right, so 1/2 times 1, or pi over 4 there. That's pi over 8 minus 0, still pi over 8. So big idea really is just kind of following these formulas, all right, and doing our best to follow along. Remember, the sine inverse formula is here, but cosine inverse is just if there's a negative in the front. Tangent inverse is here. Cotangent inverse is just if there's a negative in the front. All right, and secant inverse is here, but cosecant inverse is just that negative in the front. But if there was a negative in the front, you could just pull that out there and then use tangent inverse and keep that negative in the front. So that is an option. We can do that. So life becomes a little bit easier. All right, with that, that is it for chapter 1. Good luck with everything. If you have questions on your myopic mass, please let me know.